So this is our third and our last lecture in Internal Flow, Chapter 8. It's primarily hydrodynamics. It's primarily fluid mechanics. So let's jump into it. Here is an analytic solution that can be worked out for laminar flow when it's fully developed inside a tube or pipe where the wall has a constant heat flux boundary condition applied. It can be shown and will be shown here at the bottom of the page that the Nusselt number as a function of diameter is a constant equal to 4.36. All right, how did they get that? Well, the starting point is you say, do I know the velocity profile? If it's fully developed, sure, there it is. It's only a function of r. What is um in this equation? The mean velocity. So 2 times the mean is the maximum. And then you have this r. What's cap r right here in this equation? Cap r. Outer radius of the tube or pipe. Then we have this energy balance, but it's applicable at any point in the fluid, in the middle, all the way through to the edge. And so it's a differential energy balance statement. What does this side look like? It's the heat transfer associated with diffusion. And this is the heat transfer associated with advection. This is the energy balance equation. Let's review a little bit. If it's fully developed and you have constant wall heat flux, what does the mean temperature do as I go further and further down the pipe? Linearly increases. Why is it a straight line? Because it's constant heat flux, and for every little distance traveled, there's more heat coming in, and when heat comes in, it's realized by an increase in temperature from an energy balance. That's what it is. What about the surface temperature? If it's fully developed, H is constant. Convection coefficient is not changing. The flux is not changing. So the delta T between the surface, the local surface wall temperature, and the mean temperature is constant. So it linearly increases as well. So what you do is you say, well, I can work on this term right here in this equation, dt dx. That must be a constant. That must be the same constant that's the change in the mean temperature, the change in it's the slope, right? dt dx. The second derivative is 0. There's no concavity to that. It's a straight line. So you can replace this by the change in the mean temperature with respect to x, which is a constant. Put that in. So we replace for the u, the velocity profile, we replace for dt dx. When we get to the other boundary condition, it gets more tricky right there and separates. The solution strategy separates. For a constant wall temperature, it deviates from a constant wall heat flux solution. So this is our governing DE, stands for differential equation. It's looking for temperature as a function of R, only a function of R. Second derivative with respect to R has 2 boundary conditions. So the 2 boundary conditions, symmetry and some specified temperature, which is a function of X at the wall. So you do this, and there's a few steps right there. Separate and integrate twice, and apply your boundary conditions. And that's what you get. So you have the temperature as a function of R and X. So first of all, the surface temperature is a function of X, not a function of R. And then you have down here the constant rate of change of increase, the mean temperature, the outer radius, the fluid properties, and then you have this function of R right there. What do we want to do with it? Well, go back to the definition of what the mean temperature is, stick that into the equation. Oh boy, we're going to leave out some steps here too. You're going to take that temperature profile, the function of R, having R to the 4th and R squared, multiply it by the velocity, which is a function of R, right here, R squared, plus some constant terms. Integrate that over the area. What's the area? Little dA is 2 pi r dr from 0 to cap r. And you can get this simple equation for the mean temperature. Okay, it doesn't look that simple, but there it is. You can rearrange, put TS over on the other side, and then you recall for the global energy balance, dt, this term, the rate of change of the mean temperature with respect to x is this. Where did that come from? Again, energy balance. It's just how the heat is flowing into it. So you can substitute for dt dm, the change in the mean temperature with respect to x right there. Simplify, you find out that 11 over 48 times h d over k is equal to 1. Or you rewrite this as the Nusselt number defined as hd over k is 48 over 11, which nobody reports it as 48 over 11. They just say it's 4.36. So there you go. That's the derivation. How many minutes did it take me to do that? Right? Not too many, I hope. Hopefully it wasn't as painful as other things in your life. But there's the big conclusion. Let's try and do it for the other boundary condition where it's constant surface temperature boundary condition. First of all, I'm going to say every undergraduate heat transfer textbook that I know of doesn't do it. There's only one that does a pretty good job of it. Author is Bejan, B-E-J-A-N. But other ones, they just throw up their hands and they say, go read this textbook where they do it in detail. Kays, Crawford, Weingard in 2005. It's a lot older, but they added the third author in 2005. So there's the most recent edition, Convective Heat Mass Transfer. You can buy one of those many copies off eBay for about $10. You could buy one where it was just Kays and Crawford without the third author. It is like the resource that's quoted for this derivation as well as many other things. Well, I hate to say it, but I'm not going to go through it. I'll just allude to the challenge that Tm is an exponential where Ts is a constant. Hence, you have this, you can only say that this change in temperature with respect to x is some function of r times this dTm dx, which is a function of x, because its slope is different as I go down. Well, you put that function in there, you try and do the separate integrate, not going to work. You have to go with the numerical solution, which is iterative in nature and gets nasty. But you then want to, if you could get the numerical solution, now it's back on firm ground just like it was before, go and stick that temperature profile with the velocity profile in the calculation of the mean temperature, calculate this change, a number of other steps, and you can conclude that at the Nusselt number for fully developed laminar flow with constant wall temperature is 3.66. So if you have laminar flow, it's fully developed, you either have 4.36 or 3.66. Life's easy. So again, these are only for smooth tubes. Reynolds number has to be below 2300. That's our cutoff or criteria for transition to turbulent. And to be fully developed, you should be that far down the pipe. So this is the x to be fully developed hydrodynamically. You multiply it by the Prandtl number, and then that's the distance to be fully developed thermally. What happens if you're not fully developed? You have a significant entrance region which is developing. Well, forget the analytic expressions. Use figure out of the textbook. It's I'll just be honest, it's a little too complicated, too much time to give it on a timed exam. Hopefully you had a homework problem where you needed to do it. But the bottom line is if you have a typical very long, okay, then it mellows out to the 3.66. If it's short, if x is small, if it's short compared to the entrance region, then you're not going to get a lower local Nusselt number. You're going to get a higher local Nusselt number. The h is higher in the entrance region. So, as an engineer, a lot of times it's like, I know perfection, is nice to have, but in the interest of time, and I'm working for a company, and I need to push a product out, I need to meet deadlines, you know what? I probably know that I'm going to be able to use the fully developed term and know that it will underestimate the H. The Nusselt number will be underestimated, hence the convection coefficient will be underestimated if I use that constant value because of the entrance region will be higher Nusselt and higher H. So at least you know what side you fall on. Okay, you know how you can be more conservative in your calculations. So this would be for the entrance region. So what you would do is you would calculate this X parameter, come in here, and then you would pick up your local H, or if you want to do the average H, probably more interesting, come in there and do it. They have it for different Prandtl numbers. When you see Prandtl equal to 0.7, what does it make you think of? Come on, you've solved enough problems. What type of fluid has a Prandtl number of 0.7? All right, slow down, take a deep breath, hint, deep breath. All right, you got the hint, air. Ideal gases, around 0.7. If you're up in this range of Prandtl numbers, what type of fluid do you think that is? Water, liquids. Yeah, like water. Is water's temperature dependent Prandtl number. So, all right, ready to solve a problem? So we have a fluid, and they give us the properties of the fluid, rho, C, mu, K, Prandtl number. Just looking at it, I can look at a couple properties. I can look at this density value. What does that look like? What type of fluid? Water. Yeah, liquid. All right, and then I look at this Prandtl number. It's cold water. It's a high Prandtl number. Okay, it's temperature dependent. Prandtl number of water is temperature dependent. Okay. It's at this 0.2 meters per second. It's flowing in a tube, and it goes from 25 C to 75 C. Thin wall. This is the diameter, 12.7 millimeter, and it's 10 meters long. That's how long the tube is. So a couple things. What is this 0.2 meters per second? What did they give us? The mean velocity, use of m. So if you want to just write down use of m is 0.2 meters per second. They gave us this temperature and that temperature. What are those two fluid temperatures? Is that the T mean temperature in of 25 and the mean exit temperature of 75? That's a 2, and that's a 25 and 70. Is that what they gave us? Yeah. They give us the inner diameter. They give us the length. A uniform heat flux is maintained by electrical heater wrapped around the tube. Then you turn on the current, let the current flow through the wire, the electric heater, and it heats it up. And you have that heat would then, if it's well insulated on the outside, all go through the wall of the tube and into the fluid. So Q double prime is equal to a constant. That's our boundary condition. The fluid enters with a uniform velocity profile and a uniform temperature profile. What did they tell us in the last sentence? Don't worry about the entrance region, it's fully developed. Thermally and hydrodynamically, fully developed. Don't get bogged down thinking about, ooh, I got to worry about the entrance region. Determine the, does that say heat flux? What are they asked us to find? Q double prime? All right, what are the units, SI units on Q double prime? Watts per meter squared. That's the heat flux at the outer diameter at the wall coming into the fluid. And then what is this part B? Tube surface temperature at the tube exit. What symbol do I want for that? Tube surface at the exit. Tube surface temperature at the exit. What SI units? Degrees C. If the fluid's coming out at 75, would this temperature be greater than 75 or less than 75? Greater. Yeah, greater. All right. Well, with that, what I'm going to do is I'm going to pause. I'm going to walk around, and I want to see not your numeric answer for part A. I want to see how you would do it. Show me how you're going to calculate Q double prime for part A. And some of you will be able to get it into one simple equation with, terms like pi and r and d or t's and c's. Okay? I'm going to walk around and see what you get. All right, I'll pick it up here. So this is a big EB. Couple themes when you attack a problem. I'll apply an EB to the problem. What's the EB? Energy balance. Energy balance. We've done this a couple times. And so if I have a control volume around the whole pipe, right, I have only one in, one out. I have the flux coming in over a particular area. So I have Q double prime times pi dl. What is pi dl? The wall area of the pipe. That will give the rate at which heat is coming in. It's going to be realized by the fluid coming out at a higher temperature, m dot c t mean fluid exit minus temperature mean fluid inlet. So this is an m dot. Does that equation, where'd that come from? Oh, my equation sheet. No, it doesn't come from your equation sheet. It comes from a statement called an energy balance, conservation of energy. Is this equation even on there? It is? Okay. So here you apply Q double prime is equal to m dot c Tm exit minus Tm inlet divided by pi dl. And you know what? All those terms you can calculate. Part A is solved for. What does the answer come in at if you want to run the numbers? 12,700 watts per meter squared. Part B, the tube surface temperature at the tube exit. How am I going to calculate that? Let me pause, walk around, and let you think, because all right, in the interest of time, instead of now using an EB as a starting point, launching off in order to solve this problem, I'll use a rate equation. And in this class, there's three big rate equations. There is Q double prime is equal to minus K gradient of T. That's a great rate equation. It's called Fourier's law. It's for conduction. We have convection for this problem, so that's not the right rate equation for this problem. Okay, try another rate equation. Q double prime is equal to epsilon sigma T to the fourth. That's a great rate equation, but it's for radiation, thermal radiation. We have convection here. We want the right rate equation for convection. I'm going to pause, walk around, and see if you can pick it up from there. All right, so I'll pick it up here. So the rate equation we want to use is Q double prime is equal to H times delta T, where we have a hot surface temperature minus a cold fluid temperature. We're interested in the surface at the exit, and we need then the fluid at the exit. And so does this rate equation apply at the exit? Sure it does. So we could calculate temperature of surface at the exit is temperature mean fluid at the exit plus Q double prime divided by H. I look at that equation, I know everything but H. H, 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 H. Finally we get into something which is the main theme of this chapter, how to get H from first principles. Well, from empirical correlations. Every now and then we're lucky we get it from an analytic expression like the 3.66 and 4.36 for the Nusselt number, but that's very rare. Mostly it's empirical. How do I get the H for this problem? That's where I pause, walk around, and see what you come up with. Professor, we don't need this lecture. Answers, please. All right, so you calculate the Reynolds number, first of all, to find out if you're laminar or turbulent. We know it's pipe flow, we know the geometry. When we calculate the Reynolds number, it comes in at, did anybody calculate it? What's it come in at? 1270. Yep, that's right. So you conclude it's below 2300. It's laminar. It's with the Q double prime. Wall is constant. Hence, the Nusselt is 4.36. The Nusselt is defined as H d divided by k, so you can unravel it to get H is equal to the Nusselt k divided by d, or 4.36 times blah, blah, blah. So you come in with an H of 275 watts per meter squared degree C. Did anybody get that? You got it. Thank you very much. Anybody else? 2, 3 people? Perfect. 4 people. Great. Then we can come back here and we can calculate that the surface exit temperature is 121 degrees C. What about turbulent flow? If it's turbulent, think about the Moody diagram. Think about that Reynolds analogy, or the modified Reynolds analogy out of the previous chapter 6, which has some average Nusselt number is some friction factor F off of the y-axis divided by 8 times the Reynolds number times Prandtl to the 1/3. And I mentioned that some people had already curve fit for smooth pipes, this bottom curve out here in the turbulent region, and it curves fit like a constant Reynolds number to a power, like a 1/4 or 1/5. Constant Reynolds to the 1/5, okay? So this is the Blasius correlation. You just stuff that into here, and you could find that the Nusselt is equal to, the constant would be 0.316 divided by 8. Reynolds, not to the 1, but Reynolds to the 0.75. Prandtl to the 1/3. You know what? That'd give you a pretty good answer. But a lot of people, over the years, a lot of people had worked on correlations. And so you can use the modified Reynolds analogy. It will give you an answer. Or you can use something that's going to look a lot like it. All of the correlations are going to look a lot like this. Here they are. The Dittus-Boelter, just look at it. The constant, 0.023. Reynolds to the 4/5, that's 0.8. Prandtl, now Dittus-Boelter, when they did it, they said, well, it looks like it's more like 0.4 or 0.3, depending on if it's heating or cooling. But if you had to round it off, you just say 1/3. You're going to be close. So, but 0.4 or 0.3, depending on if the fluid's being heated or the fluid's being cooled. Let's take a look at the Sider-Tate. I think both of these are on the equation sheet available when you take the EIT exam. This one is not, but it's in textbooks, okay? So this is probably the most popular empirical convection correlation, Dittus-Boelter, turbulent flow in a pipe. All right, then this one, okay, that looks pretty close. They have the Reynolds to the same 0.8. Just put a Prandtl to the 3rd, no 0.4, 0.3 distinction. And this is a viscosity correction term. I don't know if you remember my discussion. When you see that, it's like all these other properties are calculated at the fluid temperature, not the film temperature. This is how they correct for it. This is another one. Here they use F over 8, so you would actually get the friction factor from a correlation or the Moody diagram. And away you go. These are for smooth tubes. This one will work for a smooth tube as well as a rough tube. It's a little broader, but it takes more time on an exam. So the probability of having this correlation on the exam is extremely small. I've never given an exam where I required it to be used. Professor, have you ever given an exam where this one or this one is required? Yeah. And if there's no difference, would the easier one be just as suitable? Yes, there you go. And if you take the EIT exam, or the FE exam as it's called, the Fundamentals of Engineering exam, you may see it there too. So the Dittus-Boelter, what's it for? Tube flow, turbulent flow in tubes. So William McAdams, and he published a book, and this was the third print. I don't have the first print. The first print was in 33, I believe, but I have a copy of the one done in 54. And so I know definitely what's written in that copy. So it's heat transmission and McGraw-Hill. You can buy these on eBay. They're pretty cheap. You just have to wait for somebody to post it at a Goodwill store for about $8. And you get these classic old textbooks. But anyway, in this section where he's describing both the Dittus-Boelter as well as the Sider-Tate equation, even though he doesn't use the name Dittus-Boelter, I think he does use Sider-Tate. But anyway, it says, quote-unquote, maximum deviations are plus 43 and minus 33%. What do you think about the accuracy of that? It is clear that equations of the forms of the products of powers of three dimensionless groups. What are the dimensionless groups? Nusselt, Reynolds, Prandtl. Each with the constant exponent. Constant 1, constant 0.8, constant 1/3. Are inadequate. But the world hasn't improved since 1930-something. Convection has a lot of uncertainty. Better have a good control system in there. This is inherent that you have large uncertainty, and no matter how long ago people said it's inadequate, it's still the best that's out there, believe me. Just as that's the way it is. That's empirical correlations. Now let's move away from round. Let's do non-round in laminar and then non-round in turbulent. Got it? So we have, if you have laminar fully developed flow for a box or rectangle or different shapes, guess what? You have the uniform heat flux. There's your Nusselt number, your constant Nusselt number. If you have uniform surface temperature, there's your uniform Nusselt number. Do you recognize those two top? 4.36, 3.66? Sure. So that's nice that they put that in the top. So yeah, for round tubes, oh yeah, I recognize these two values. Okay, non-circular tube, like a rectangle, like a duct. And you have turbulent flow, meaning you calculate that Reynolds number and it's greater than 2300. What do you do? Well, first of all, you need to use that hydraulic diameter, d sub h, and use the correlation for round tubes. D sub h, hey, I saw that in fluid mechanics. What is the hydraulic diameter defined as? 4a, sometimes they put a c on that a, but sometimes they don't, divided by p. All right, what is the a for? Cross-sectional area. If somebody said this had height h and width w, what would be the cross-sectional area for flow down that duct? As an example, the AC would be the product of h times w. All right. What is P? Perimeter for this duct right here. What is that perimeter? 2h and 2 w's. W on the bottom, W on the top, H on this side, H on that side. So you calculate the hydraulic diameter. Use that to calculate the Reynolds number. Check if you're turbulent or not. If you're laminar, go to the other table. If you're turbulent, go out and use Dittus-Boelter. A lot of times in these systems, they'll have some sort of treatment on the inner surface or even outer surface, but here we're talking about inflow inside. So here they have some fins on the inside, or they'll take a coil spring and insert it, or they'll take a twisted tape and insert it, and that's all to make the flow rip into the wall and to promote the heat transfer. Well, you're going to increase the H, but you're going to increase the pressure drop too, the pressure loss. So there's a penalty, there's a cost to it. But you'll see these enhancements out there in practice. It's just mathematically challenging and it's all empirically based, so you just have to look for the right correlation. Not on the exam. Do you like that? There you go, not on the exam. let's solve this problem. Water flows at this flow rate. Is that a mass flow rate? Sure, that's a mass flow rate. And it's inside this diameter tube. It's a circular tube with the length of this. So we're given the diameter, given the length, given the mass flow rate. It's subject to a wall heat flux of 20,000 watts per meter squared. So Q double prime is constant. All right. The mean inlet water temperature is 29 degrees C. TM inlet, 29 degrees C. Determine the mean outlet water temperature. Again, struggle with what symbol do I want for that? How about this one? Temperature mean at the exit. And what units do I want it in? Degrees C. And then what is that tube wall temperature at x equal to L? So this is the tube surface temperature at the exit in degrees C. So for water, use this value of density, specific heat, viscosity, conductivity, Prandtl number. So how am I going to solve for this problem? I'll pause, walk around, and see how far you can get. So I'll pick it up here. So since Q double prime is constant and I'm interested in the mean outlet temperature, can I do the EB approach? Energy balance, which is just Q double prime times some perimeter times length equal to the mass flow rate, specific heat, temperature mean exit minus temperature mean inlet. Hey, deja vu, haven't I seen this before? Well, there's only so many concepts that we can test you over. Energy conservation, energy balance. That's it, right? That's very important. So if you want, you then calculate the temperature of the mean at the exit, and that comes in at 32.0 degrees C. Did I need to know H in order to solve that problem? No, I didn't. Okay, but what about the tube wall temperature at x equal to L? Need H. Same concept, so we go to our famous rate equation, our convection rate equation. So Q double prime is equal to H T surface at the exit minus T mean at the exit. And we've done this before. Surface at the exit is mean fluid at the exit plus Q double prime divided by H. I need that H. H is equal to the Nusselt K divided by D. I need the Nusselt. To get the Nusselt, I have to calculate the Reynolds number. When I go and I calculate the Reynolds number, anybody get around 780? 1, 2, 3, 4, 5. 5 people did? 6? Okay. So this says laminar. You can check the length, but if you check the distance to be fully developed hydrodynamically, that comes in at about 7.8 millimeters. How do I get that? 120 the diameter times the Reynolds number. That's not a large distance. But if you get X to be fully developed thermally, you multiply 7.8 millimeters by the Prandtl number, which is about 5.5, and you pick up that it's 43 millimeters. So it's by the time you get to 100 millimeters, it's fully developed both thermally and hydrodynamically. Hence, H can be calculated using, or the Nusselt number can be calculated using the constant for a round tube. It's a heat flux, so that's 4.36. So you come up here, now that you know it's 4.36, put in the conductivity, put in the diameter, and you get an H value of 13,450 watts per meter squared degree C, very large. Then you can come up and calculate the exit surface temperature, and it's 33 point around 5 degrees C. Ready to move on? Air. Air at 12 degrees C enters a 2-meter long rectangular duct. It's a rectangular duct, so we're going to have a definitely hydraulic diameter consideration. And it's 75 millimeters by 150. So 75 by 150, it looks like that. This is 150 millimeters that way. And this is 75 millimeters, and the flow goes down the duct like that. It's maintained at a constant temperature of 127. The air flow rate is given, 0.1 kilogram per second. Determine, now this is, on this problem I messed up. That should have been before. Determine for part A the air outlet temperature. Then for part B, the heat transfer rate to the air. And then for part C, the duct wall temperature at the outlet. So for part A, the temperature mean of the air exiting in degrees C. The heat transfer rate to the air, that's going to be Q in units of watts. And for part C, the duct wall temperature at the outlet, temperature surface at the exit, degrees C. Right, so how am I going to get the mean temperature at the exit? First of all, maybe you want to even sketch it like this. You say, well, this is temperature here. I'm going to plot, first of all, 127 degrees C. That's our temperature of the surface, and it's constant down the length. It's not a constant heat flux, it's a constant surface temperature. And our fluid comes in at a whopping 12 degrees C. Does it stay at 12 degrees C, the fluid? Does it linearly? No, we played this game. What does it look like? What is the shape of that curve? Exponential, right? And from an energy balance, a differential energy balance, we were able to get a differential equation with the boundary condition and integrate and solve. And so we got that solution, which had an exponential function in it. What did that function look like? It looked like the temperature of the fluid, the mean fluid temperature at any location X down the pipe is going to be less than that wall temperature by the difference between the wall and the inlet fluid temperature multiplied by exponential, and then here it's a minus. You have a H PL divided by M dot C, or instead of PL, it's a PX. Make sense? All right, let's make sure we understand every term. What is this TS? Surface temperature of that duct. What is TMN? Inlet mean fluid temperature. M dot, mass flow rate, specific heat. The convection coefficient, may have to work to get that. May have to get the Reynolds number, then the Nusselt number, then get the H. What is this cap P? Perimeter. And X is the distance. So if I wanted to get the outlet, X is L. True? If I wanted to mean outlet temperature. So, okay. We have, like I do this, I'll say, I know this one, I know that one, I know this one. How about the mass flow rate? That was right here. True? I know the mass flow rate. How about the specific heat? I know it. It's given in the properties at the bottom of the problem. How about the perimeter, P? We just did that one. It's 2H plus 2 W's. And X, that's the length. It's 2 meters long. Guess what? Everything is known except for H. So how do we get H? First, we'll get the hydraulic diameter. Then we'll use that to get the Reynolds number based on the hydraulic diameter. Can I pause for a minute and you get the hydraulic diameter for this problem? And then if you get it, go ahead and get the Reynolds number. Sorry, I'm going a little slow. I only got about 10 minutes left. All right, so this hydraulic diameter, after you work it out, the 4 cross-sectional area perimeter comes in at 0.10 meter, true? Now we need to get this Reynolds number using hydraulic diameter. So it's going to be rho u mean hydraulic diameter divided by mu. Do you agree? Well, now, every now and then I'll say, oh, for a round tube, that's 4 m dot over pi d mu. For a round tube. Is this round? Round only. All right, but you could use the same type of logic to get there, but you won't get to the, you'll get to the right answer, not assuming it's wrong. Or if you assumed it's round, it's really wrong. So what do? Is you multiply by the cross-sectional area. That's the same area as right there, true? And so I have to divide by the cross-sectional area. Okay, but what is rho u a mean times the cross-sectional area? M dot. Perfect. So you can get this by doing m dot times the hydraulic diameter divided by the viscosity and then the cross-sectional area. Both the hydraulic diameter and the cross-sectional area you had to already have done. Okay. In this case, what the cross-sectional area is, the 75 times the 150 millimeters squared. So you'll just convert that from millimeters squared to meters squared, and away you go. When you do this, the Reynolds number comes in at 42,735. So I pause for a minute. What do you conclude about that Reynolds number? Turbulent flow. What correlation would you like to use for turbulent flow? The dB, the Dittus-Boelter. So you get that the Nusselt is 0.023. Reynolds to the 0.8. Is the fluid being heated or cooled? That'll determine that exponent on the Prandtl number. Again, I don't make a big deal of it, but let's be accurate. Use the correlation the way it was published. 0.4 if it's being heated. And that Nusselt number comes in at 101. Once I know the Nusselt number, then H is equal to the Nusselt K divided by D. My Nusselt number allows me to get an H of 30 watts per meter squared Kelvin or degree C. Not a very large H, but it's air. Air is a lot lower H because a lot lower thermal conductivity. So now I can calculate this H. I come back to this equation, put in my H, and I can calculate the mean temperature of the fluid that exits. It goes out at 39.2 degrees C. Do you really think I'd trust that 0.2 degrees C? No, but I'm going to give it to you to 3 significant digits. There it is. Okay. Now, what about the heat transfer to the air? Go back to an overall energy balance. So Q, what comes into the air, is equal to mass flow rate specific heat temperature mean exit minus temperature mean inlet. Now, I'm just looking for Q, and the answer is total watts, not Q double prime, just Q in watts. It's even easier. So we've calculated that the Q is 2,750 watts. It's 127 degrees C. All right, we have 5 minutes left. Basically, we skip these parts. Convection correlations, highly empirical, non-circular tubes. We know how to handle. Just solve the problem like that. Turbulent flow, Dittus-Boelter is the way to go. Laminar flow, 4.36 and 3.66. Depending on if Q double prime is a constant or temperature wall or temperature surface is a constant. Don't forget energy balance. Thank you very much for your attention.